So in this talk, I will be talking of something a bit different than what we've seen in the conference so far. So it's mostly related to this concept of bound state in the continuum in dielectric nanophotonic structures. And of course, some interest in also looking at the effects of coupling 2D materials to this type of structures. So in terms of fundamentals, let's say, so we heard something about it in the next in the last days. Here we're dealing with what are basically nanostructured high-index dielectrics, such as silicon or gallium phosphide in the and in this case, like you can think about it as plasmonic non-antennas, but here, we don't have any free electron gas, so we're not actually exciting any plasmons, but we're mostly exciting so-called mere resonances in these nanostructured dielectrics, which are nothing but induced currents by light. One of the main difference here is that we have both an electric and a magnetic characters of these resonances, and also, of course, like dipolar and multipolar resonances. And this leads us to a very interesting idea of be able to couple and interfere these resonances in single nanostructures in order to achieve new photonic states, basically. In this terms, one of the interests is that to engineer some non-radiating nanophotonic states, which you can see one here. So this is like anapole states in a single nanodisk, which basically does not couple to the far field. So we can confine more strongly light inside this resonator by simply making interfere like a electric dipole resonance and a toroidal dipole resonance. Other idea in single nanostructures is the so-called supercavity mode, which was shown a few years ago in a single nanodisk, basically. And here we have instead like a strong coupling between the Fabry-Perot mode in the in one of the dimension of the structure and the mere resonance of the structure themselves. What leads this is basically like a high quality factor resonance, which has been linked to the concept of bound states in the continuum. So to give a very quick introduction to this concept, we're basically not looking at something new. So it's something that has been theorized like in the 20s. So at the beginning, let's say, or during like the gold age of quantum mechanics. And what is the concept is basically that if we have an Hamiltonian, we can find some solution of this Hamiltonian that are basically bound states, but in a continuum of states. So in a region where we have like a continuum of energy levels, and basically linked to a dark mode, which does not couple to a radiation, and basically at the end having like an infinite lifetime, and of course then an infinite quality factor. So real bound state in the continuum is actually quite useless in our case because we cannot couple to it, and so the best and let's say that like the concept of this bound state in continuum in nanophotonics is actually trying to break the symmetry of our system, so we can create the so-called symmetry protected bound state in the continuum, which can couple to light. So we can have this coupling to light and end up basically in practice collapsing to a Fanon resonance in the spectrum. And a small deviation of the symmetry creates the highest quality factor. And then if we increase the asymmetry, basically we then reduce the quality factor. And with this concept has been quite studied in dielectric metasurfaces. So this is like one of the fundamental, let's say, work on this topic, where they show that if we can create like a metasurface with this elliptical resonator, and we tilt the angle between them, we can actually induce very high quality factor resonances for the smallest asymmetries, which are indeed basically created by the interference of the electrical dipoles in each of these resonators. As we increase the symmetry, our bound state in continuum, which now we call quasi-bound state in continuum, since it's not really like this BIC mode. You can see that like as we tilt the two structures, and thus we increase the asymmetry, this bond setting continuum like drops its quality factor values and starts to like also become basically like a broader and broader resonance. In the case of this symmetry protected bond setting continuum, we can also find out that we have this kind of bond setting continuum in different types of structures. So you can see here, like in this figure on the right, different types of asymmetrical structure, but for my purpose here, we will focus on this pair of nanorods. So if you have these two nanorods with the same length, we basically have fundamentally a bond set in the continuum. But if we just break the symmetry by reducing the size of one of these two nanorods, we actually introduce this symmetry breaking, and thus the creation of this high quality factor resonances, which has been fundamentally shown that they have proportional. So the quality factor is proportional to the asymmetry, as you see here, like 1 over the asymmetry parameter square, basically. And of course, like we said, like we have high quality factor resonances. So what are they useful for? Here are some examples. So there have been interest in molecular sensing for this structure, since the near field is mostly located outside of the resonator. So we can couple light to, I mean, we can have interaction of light with, for instance, here some molecules on top of this these metasurfaces. But of course, my interest is mostly related on photonics and optics, and so we can actually think about using these states for lasing, control of quantum optical properties of photons, or in this case, also like enhancing basically nonlinear optics, since we can confine more light inside a resonator and thus increase the electric fields and near fields. So I said, like the main like platforms so far shown in nanophotonics for these BIC states are either like single particles, which have of course like very small footprints. So we have like a small particles, but they have some problems. First of all, like that we need to really be able to engineer the interference between modes in the single particle and also substrate related effects. And at the same time, in order like to excite this bond set in the continuum, we also need to have complex polarization excitations, in this case, azimuthal polarization for single cylinders. And also the near field is mostly confined inside the resonator. So it's very good for instance, frequency conversion, but for coupling luminescent material to the structure is actually not the best. And the second is actually metasurfaces. So the second platform is just like a large two-dimensional array of nanoresonators. So it's good at, because basically like we have the interference between the whole system and strong near fields outside of the resonator, so in between these nanoantennas basically. But we require large area samples, and again we need to basically use a certain degree of polarization. In this case, we need to be parallel to the axis of the rod, so we need to have a linear polarization to excite these BIC states. Now, the idea of the work here and what we've been doing in Munich is actually trying to coalesce these two ideas into a new formal, and that is exactly this so-called radial bond set in the continuum. So you can think about it just taking a line of our metasurface and close it into a ring and creating somehow like a infinite one-dimensional type of system. And we show that this is indeed like a very appealing platform, because we have control over the line width and wavelengths of the resonances through different parameters. So you see radius, length of the rods, and number of resonators. And most of all, like we also have like these interesting features that it's completely polarized independent. So we can fully like excite it without the need of any Taylor polarization. So you can just shine light on it and you will see this this mode arising. So to have like another picture of this quasi-BIC resonances in the states, we can look again at this symmetric case. So we can here, of course, is all simulation. So I will show you later the fabrication and so on. So for simulation, if we have no asymmetry, you can see that the state doesn't show any near field. So we basically have no resonance in the case of a fully symmetric structure. But as soon as we break the symmetry, just of like in this case like 25 nanometer on as a difference in length between the rods. You see that like instead now we can excite a near field around the around the ring, and the near field also decays with the increasing asymmetry, meaning that again we probably are indeed like in the case of this excited this quasi-BIC mode. And looking at more simulation, how does the resonance basically look in the spectrum? Is this high quality factor resonance in the case of like the smallest asymmetries with quality factor that theoretically we predict to be up to 1400. But interesting, like as you can see here, we still have this characteristic dependence of the Q factor to the asymmetry of 1 over the symmetry parameter squared, which is exactly like the expected value for symmetry protected quasi-BIC modes. And we then fabricated them in with the common top-down techniques, so using amorphous silicon and electron beam lithography to draw the structure, and reactive ion etching to etch the structure into our in our substrate, and then of course like did some optical characterization. So here I'll show you the parameter space that we can use to tailor the resonances of this rings. So first of all, of course, we have a ring, so we can change the radius, and you can see clearly how we can shift our high quality factor resonance in wavelength by simply increasing the radius, so increasing the distance between each resonator in this case. But we can then also, of course, change the resonator length, as you can see here, or even the number of resonator composing the ring itself. And in this case, we also checked, of course, like if we can see these high quality factor resonances. So we just look at the different asymmetries, and we then tailor the radius in here. So like when you see the difference of the various resonances, just changing the radius, but with the fixed asymmetry. And again, we can see that the highest quality factors, so the narrowest lines, are indeed the one with the slowest asymmetry, in this case of 25 nanometer, and increasing as we increase the asymmetry parameter. And if we plot this data, so we plot them in this three-dimensional plot with the function of the asymmetry, the radius, and the quality factor we extract with the again Fano fitting like the resonance with the Fano parameters. You can see that indeed, like we observe like highest quality factor in the case of the smallest asymmetry, arriving to approximately like above 500 quality factor. And we also then probe the polarization invariance of this resonance. So we just take our light, we polarize it linearly, and we rotate it in respected to the ring. And as you can see from the plot on the bottom right, is actually quite stable. So this quality factor, it's quite invariant. So we'll always see some higher than 200 quality factor for this structure, which of course has some not perfect asymmetries because of imperfection in the fabrication, so design and etching of the structure itself. So as said, this is like a very nice and interesting platform. So what we wanted to do is that can we actually do something with the 2D materials? And in this case, we wanted to look at the generation of second harmonic light from our monolayer in this case. And going quickly on second harmonic generation is basically like doubling the frequency of the incoming light through a nonlinear material. And in the case of second harmonic generation, we always need a non-centrosymmetric system. And of course, transition method chalcogenides are very interesting because this broken inversion symmetry in monolayer is one of the nice characteristics of this material. But instead, we have a second layer rotated 180 degrees in the case of natural occurring material. We then have a zero efficiency for this second harmonic generation, which leads to possible, of course, like interesting physics. I mean, you can also like easily change this parameter. But one of the other things that is interesting of two-dimensional material is the fact that you have less than 1 nanometer material, and this second harmonic efficiency is quite high, and also like it does not require as any phase matching compared to common materials and common crystal used for this second harmonic generation. And then finally, another interesting features of second harmonic generation is that we can use it to study strain or have an effect on the between strain and the efficiency, of course, because by changing the parameters of our lattice, we change the symmetry of the system and also the efficiency of this nonlinear process, which, as you can see, it actually decreases as we stretch our material, which I will show you later. It's interesting somehow. And finally, so how do we couple the 2D materials to these dielectric nanostructures? We have some works on this. Like we actually show some few interesting physical phenomena from the interaction between two-dimensional semiconductors and electric nanophotonics. But the idea is quite simple. So we just take our exfoliated monolayer and we just transfer it with a all dry transfer technique on top of these nanostructures. And as you can see, it quite works fine. So like we can actually couple very close to the near field our excitonic material. And of course, then we have to tailor the resonance of our cavity to the exciton in the case. But with this approach, we actually show some enhanced light matter interaction and weak coupling of the two-dimensional excitons and two-dimensional quantum emitters to these dielectric cavities, and also studied the properties of strain in the system. So as you can see, we have like a lot of strain, of course, because we're stretching a rock on top of another rock. So that's really like interesting to also look at this effect. And you can look at more information in these papers, basically. And what we did is then, as said, like we just transferred a monolayer of molybdenum diselenide in this case on our ring structure. And you can see from the AFM and the bright field and field imaging that we have a nice coverage of the system. So the monolayer is sitting on top of it and sticks, of course, due to this van der Waals interaction. And we probed the sample with the use of a femtosecond pulse laser. So we can tune the wavelength and then look basically at the second harmonic generation as a function of the wavelength. So we first of all tune it to the bound state in the continuum resonance and observe an extremely nice effect where we have an enhanced second harmonic generation only where our 2D material is in contact with the ring structure. And we also confirm that this is indeed like second harmonic generation signal for polarization measurements that you see here, and also of course from power dependence. So we see this quadratic dependence. But the interesting feature is that if we then move our excitation wavelength to different spectral region, we instead observe the different effects. So just to quickly go through here, we have our transmittance spectrum of the sample. So we have here at roughly 745 nanometers our bound state in the continuum resonance. At around 790 nanometers, our exciton resonance of the molybdenum diselenide itself. And so we look at the so we probe basically the sample with the close to resonance to the with wavelength close to the resonance of the exciton, far off in the red, and then at the BIC resonance. And as you can see, we have this striking effect where the second harmonic generation is enhanced only at the bound state in the continuum resonance, and also we observe this strain effect on the second harmonic generation in studying the other wavelength ranges, where we have instead that the second harmonic generation signal on top of the ring is damped instead than enhanced. So what it means that we exactly observe this enhancement of the second harmonic generation as a due to the near field coupling of the 2D semiconductor to the bound state BIC resonance, and highly localized again, so offering like a new approach to indeed like study the nonlinear effect and in 2D semiconductors. And as I finally want to show that, as we said, like we can actually look at the dependence of this resonance as a function of the linear polarization. So in this case, we set our linear polarization. I mean, we set a laser to linear polarized laser and reduced quite a lot the power in order like to observe this nice slopes. And as you can see, as we rotate of 90 degrees the polarization of the laser, we also observe this enhancement in the second harmonic signal. And in conclusion, then we indeed like look towards like this new platform for quasi-bond set in the continuum, offering a lot of parameters to tune line width and wavelength, and also having an extremely small footprint so that you can think about like making like rings inside of rings and inside of rings. And we also then probe this for like sensing and second harmonic enhancement in 2D semiconductor. And with this, thank you for listening. And I also would like to acknowledge all the people that collaborated to this work, and most of all, Luca Kuhner, who really pushed this fabrication and project the farthest, let's say. And so, thanks.
Thank you very much, Luca. Very, very nice talk.
Thanks.
Do we have questions in the audience? So I have a question. I was wondering, what if you use in plane anisotropic material? Then maybe you could arrange this antenna with the same length. Then they would respond different in different directions. Have you thought about this?
Well, not yet, because we really wanted to prove that this is an option, but the main problem was then indeed like trying to, how do we couple the materials? The main interest was actually trying to see a new option for like this coupling. So transferring on top, or at this point, growing it into it or outside of it. So you can think about many options. And most of all, you can also think about imprinting this design inside the material itself without having the need of growing the antennas themselves.
Okay, thank you. I think it's a very smart approach. I mean, I like a lot this idea.
Thanks.
So, do I have more questions? If not, let's thank again the speaker, all the speakers. Now we're coming.